magnetic effect of current, EMI and AC. Right. So without wasting time, students, I'll start the numerical first. So this is my dear first numerical. What's its first numerical? A current carrying I, students, a current carrying I flows along a thin wire set as a regular polygon of n sides, which can be inscribed into a circle of radius r. Find the magnetic induction at the center of the polygon. Okay, fine. So come to the point, my dear. So here for this condition, what is the point which you can take in consideration? Okay, yes beta, it's literally very easy, my dear. Yes, very easy, student. We'll go through here. Egypt of Alsi here only. So student, what's question? I hope all of you got it here. A current carrying I flows along a thin wire shaped as a regular polygon, right? So student, you can take a regular polygon. Student, solution for these questions. Yes. So this is, students, you can take okay, fine. Students, here this I make complete loop, but it's a n sides. It's what, students? N sides, right? So just take in consideration flow of current, it's correct only. Current remains same, bacha, already mentioned the questions. A current I flows along a thin wire shaped as a regular polygon of n sides. So I make completely, but you can also take a regular polygon. So let us suppose, students, I'm calling this point is O. O is nothing, student. It's, you can say, what? Center of this polygon, right? So student, for this condition, just we'll go through this. So this, because sides is n, students, so you can say easily this is beta how much? 2 pi by n. Student, you can write here this angle beta how much? This is, students, you can easily say this is 2 pi by n. So student, just make one perpendicular. So you can write this angle is 90. This also beta is 90 only. So this angle you can see pi by n beta. This is what? Also you can see this is pi by n, right? Okay. This angle, student, also pi by n beta. This angle also you can see remains pi by n only. Okay. So beta, just for better clarification, I'm going to just this part keep it out. Yes, beta, be focused here only. Be focused, students, here only. Yes. Now I'll give you beta a satisfactory solution here. I'll give time. I'll take more time, students, as usual, with another difficulty, but I'll give you a satisfactory solution. So this angle, student, pi by n, as I said. This angle is also you can see this is remains same, my dear, which is what? Pi by n only, right? Okay, fine. So student, for this area, I'll do little yes, student, you can easily understand the things. Yes. Okay. So now beta, for further here, what's the point you can take in consideration? Yes. Let us suppose beta, this is point O I have taken. This is point A. So this is O and this is A. Beta, what you can say? This is what? Perpendicular distance. This is what? Perpendicular distance. So you can take beta, this is radius r, this is radius r, right? Everywhere, student, radius remains r only, right? So no beta, because here I'm going to apply a formula, magnetic field due to finite length of current carrying wire. I hope all of you remember. So beta, first I wanted to write a formula First student, now I'm going to write formula here which I'll apply over here. Magnetic field due to finite length of current carrying wire, what is student, mu naught into I beta g 4 pi d. This is sin theta 1 plus student this is sin theta 2. I hope yeah, all of you remember this formulas. Magnetic field due to what, finite length of current carrying wire, mu naught into I by 4 pi d sin theta 1 plus sin theta 2. Okay, so beta for this formula, continue further, moving ahead, solution of this question. We must know what is d, what is theta 1, what is theta 2. So d is nothing beta, d is nothing there, what you can say, it's a perpendicular distance. So you can write beta everywhere, this is remains r only, this is what my dear remains r only. So you can take component r cos. So you can see this perpendicular distance, students, here I'm writing this is OA, which is students perpendicular distance, so this is OA, which is equals to r cos of pi n. What are students? So finally I got one answer, that is g is equals to r cos pi n. Student, here you can write here from this diagram, you can easily say, my dear, from this diagram you can easily say, my dear, sir, theta 1 is equals to theta 2, which is equals to pi by n. Right, student? But this value you can fit over there, students, in above equations. So now student, magnetic field due to finite length of current carrying wire, you can write mu naught into I by 4 pi, and d is what, students? It's r cos of pi upon n. Okay, and this is a sine, students, sin theta 1. So sin pi by n plus student sin theta 1 plus sin theta 2, my dear. So this is also remains sin pi by n. You can just do further calculations, student. That is magnetic field B, which is equals to mu naught into I by 4 pi, mu naught into I upon beta 4 pi. This is r cos pi by n. So just simply you can add students. So this is twice of sine, this is pi by n. You can see student, this expression you have to see carefully, then you can see, sir, this cos pi and sin pi becomes tan pi. So student, finally you can write here above expression, this you can also write mu naught into I, students, this is 4 pi r into 2 sin pi by cos pi beta. You can see, student, this is tan pi by n. Right, so this is beta, I can say desired answer of these questions. 2 beta you can say cancel. So magnetic field, students, you can write mu naught into I by 2 pi r, this is tan pi upon n. Right, but no, student, this is here you found result for, I can say, one wire, but we wish to find for entire wire. So what you can do, students, due to whole polygon, students, magnetic field at center O, so just this magnetic field beta, just you have to multiply magnetic field, students. Here I'm writing it for entire answer in this box. Magnetic field due to what, students? Due to n sides of polygon at point O. Magnetic field beta, I can see this is magnetic field total So this is n times of B, my dear, n times of B students. B already I found from here student. B already I found here Vacha. So you can write magnetic field total, which is equals to n mu naught into I student. This is 2 pi r into beta tan pi by n, right? So this is answer beta for this question student. This is answer for this question. So it's a good question student, no doubt at all. It's a good question, my dear, right? So have a look at the next questions here. Yes, Vitaji, have a look at next questions, right? So what's the next question student? Okay. Beta, take one snapshot. This. Okay, fine. Come. Beta, see next question here. A current I flows in a thin wall long half tube of fur, which cross section is shown in the figure. Students, you can take. This is half tube. Yes, beta. Next questions. A current I flows in a thin wall half tube, or you can leave it here. These questions. Yes. Next question, beta. Figure. Yes, we'll go through this question here. Beta, we have to find in these questions magnetic field. Beta, magnetic field somewhere you can also get it. That is magnetic induction. So both are remain same. So don't be hesitate. Right. Magnetic induction at a point. Beta, you can write 0, 0, z due to the wire. Okay, so student, let us suppose it's diagram student mentioned in these questions. This is x-axis, this is y-axis, z-axis. Student, current is basically flowing in this wire. Beta, current is flowing beta, you can see along x-axis and going to y-axis. Yes, beta, you can take in consideration like this. Yes, my dear. Right. So this is students, current coming from here and going like this. Right, na beta? Current coming beta here and beta going like this. So beta, what you can say for these conditions? I remains the same. I remains the same. I remains the same. Okay. Beta, this point you can take as R as a point. So you need to find magnetic field at here. Let us say I'm calling point P. And point B is coordinate 0, 0, z. Student, there is a, I can say, current carrying wire, which is mentioned in the questions. Right. So determine the magnetic induction at point P. Current value remains same. Due to wire along x-axis, magnetic field at P. Because wire here bacha body. Right. So magnetic field at P for this current carrying wire. What we can say with Shepard, because you know how can we find direction here, because magnetic field we are finding. So beta G, this always you can put your hand like this, always you put your thumb in the directions of current and call the finger where you want to find, right beta party. So this is what beta we can see. Yeah, this again here goes like this. This is beta in upward by axis here. Okay. Beta, for this one here, what we can say, this is for magnetic field in x-axis. Okay, so beta, here I'm writing it in solution. Magnetic field at point P due to wire along x-axis. So magnetic field at point P due to wire along x-axis. What is beta magnetic field due to semi-infinite wire? I hope all of you remember V naught into I by 4 pi. mu naught into I by 4 pi बच्चा. So you can say this is mu naught into I अपन बच्चा this is 4 pi z here beta this is what plus j cap. Then beta magnetic field along by axis here. This is formula remains same, but this is coming beta this direction here. So magnetic field at point P due to current carrying in by directions. So this is mu naught into I by 4 by z plus I cap. We used to find what is the net magnetic field over here. So here beta you will get magnetic field due to these two wires. Due to these two wires. So this is magnetic field at point P. You can write magnetic field at point P due to current carrying wire X plus magnetic field at point P due to current carrying wire in by directions. So students, finally you can write magnetic field at point P. This is what, my dear? Mu naught into I by 4 pi z plus mu naught into I beta this is you can say which j cap and this is beta j I cap 4 pi z. So finally beta you can take it common here, few identical terms, mu naught into I by 4 pi z I cap plus j cap. So this is answer with, or you can also write it without direction. Without this is answer with respect to direction here, because both are what you can say perpendicular to each other. If both are perpendicular, so finally you can write, my dear, magnetic field is equals to what? A square, because you can see beta one in this direction here, one in this direction, so both are 90 degree. You can say A square plus B square plus 2AB cos theta बच्चा. So simply you can write beta in terms of magnitude root 2 students mu naught into I by beta 4 pi z. So this answer also correct only. Both answer correct only, student. It's a totally depends on my dear options in the paper hall. It totally depends on the, I can say, options on the paper hall. In the paper hall, yeah. Okay, fine. Now बच्चा जी have a look at next questions. Have a look बच्चा जी next question. Okay. Now students, as I said here, in this class I'll discuss only numerical. So next numerical beta I'm going to take based on the students flux or magnetic flux. That is chapter's name, you can say EMI, right? So what's question, student? Listen carefully. Okay, student, current. I'll write these questions here. Current, a current I, you can take it, it's current capital I, flows in a long straight wire, student, of radius capital R, determine the student determine the magnetic flux through half of wires cross section half of wire cross section in radial plane, radial plane of length I, right student? So just we'll go through this here once. Yes beta, once here let's just go through questions once. Again, a current I flows in a long straight wire of radius r. Determine the magnetic flux through half of wires cross section in radial plane of length I. Okay, length also I will say, right? Length also length I. Oh yeah, it's collide now. You can take here something. Length L beta I can take. Length L, current IR. Right student, have a look. How can you find here? Let us suppose student, for the solution, a current I flows along straight wire, right? So you can take beta in consideration. This is long straight wire. This is what, my dear? Long straight wire. Okay. We have to find magnetic flux for half of the wire, not for entire. So let us say student, calling this is axis of the cylindrical wire. This is axis of the cylindrical wire. Okay, so if this is axis here and side is mentioned, you can take beta. So what's the side, my dear? Side of the wire here, length of the wire, not side of the wire. Length of the wire, my dear, this is what, L only. If you remember your basic point, I can say how to find, student, how to find basically a center of mass of a rod, center of, you can say a moment of inertia of a rod, how to find gravitational field on the axis of rod. If these all things you remember, so beta behalf of that questions, you can do this question in a same day. What is it? You have to move x. Yes beta, we have to work students only half out of this infinite straight wire. This part we have to work only. So what you can say, my dear, you have to move x. Student, this is a primary thing. You have to move x and take element dx. Yes beta, you have to move x and take element dx. You have to move x and take element dx. Okay, so this element beta, you can write, my dear, it's a dx only. It's what you can say, dx only. Fine. So due to elemental strip beta, I wanted to write what is magnetic field. So students, here you can say magnetic field due to elemental strip. This is what is student, magnetic field due to semi-infinite current carrying wire, mu naught into beta I by 4 pi t. And for cylindrical wire inside point, if you remember k cube x from electrostatics, so here beta, what's the formula? Mu naught into I r upon 2 pi r square. Mu naught into I r upon 2 pi r square. So what I can write beta, magnetic field for elemental strip. This is what, my dear? Mu naught into I upon x upon beta j 2 pi r square. Right. So this x, it's very less with respect to you can say radius of the cylindrical wire, right? Okay, we wish to find flux here. So this because it's a small elemental strip, so here is what I'm going to write. This is what, d phi. I hope you all of you remember I hope beta all of you remember here. That is what magnetic flux beta. What we can say for elemental strip, that is V into beta J dA. Beta Jai Sri Sham. Beta, this is what you can say B into dA. B beta already we found. What's the dA? Length into breadth. It's a strip here, rectangle. Length into breadth bacha. So here, my dear, you can write d phi is equals to mu naught into I upon beta J 2 pi r square. This is L into beta dx into x here. Now onwards, it's very easy to do. Yes, beta. This we can apply a limit because we wish to find total flux. So beta, I can say total flux student integrate here d phi. This is mu naught into I into L 2 pi r square x into dx limit beta 0 to r. So this is flux total student mu naught into I L upon 2 pi r square x square by 2 0 to r beta limit. So we can write here flux total, my dear. This is student flux total student. What you can see mu naught into I L upon 2 pi r square x replace with r square by 2. So this is cancel here. So finally you can write as answer of this questions mu naught into I bacha. This is L upon beta J 4 pi. So this is the flux total for the half straight current carrying wire. For the half straight current carrying wire, right, my dear? Okay. So just this is the beta. I can see I'm just solving questions little slow, so that you are not in front of me, so that you can ask multiple questions. So how this is. But still, I'm explaining all the things, student. Still, I'm explaining here all the things, right? So beta, just move on here. Next numerical. Yes, beta, take snapshot first here. Student takes snapshot first. Student, right? Okay. Next beta, again here I can see very standard and very common questions to do. So what's the question there? You can say there is a disk. There is a thin disk, right? And that is non-conducting disk. And those disk is what? Rotating. Right. I'll write once your question is written so that you can easily understand here and feel comfortable. Class at physics 1 live stream. So this is the next question, and it's I can see beta very good question here. Very good question, student. So what question, student? A non-conducting thin disk of radius capital R of radius, student. Capital R is uniformly charged with surface charge density. Student, surface charge density sigma coulomb per meter square. The disk rotates about its about its central axis at angular speed omega. Find the magnetic induction. Find the magnetic induction at center of disk and its magnetic moment. Find magnetic induction at center of disk and its magnetic moment. Okay, student, God bless you for your reaction. Magnetic moment. Okay, fine. So बच्चा जी, for this condition here. Okay, fine. बच्चा, come to the point. So here beta, we'll go through this here. Again beta, it's a good question, student. So what question is, I'll repeat once again. A non-conducting thin disk of radius capital R is uniform charge with surface charge density sigma coulomb per meter square. The disk rotates about its central axis at angular speed omega. Find magnetic induction, means we have to find B at center of disk and its magnetic moment. Okay, my dear. So we have to find two things here. Listen here carefully. Listen carefully, student. So what's the solution? Have a look. They mention thin disk here. Again, Peter, I can say those students easily can do these questions who has, I can say, pre-understanding like how to find center of mass of a disk, how to find moment of inertia of a disk. Those candidates can do easily questions. Those students can do easily questions, right? Okay. Student, are you from in which class you are? 12th class, no? 12th class tomorrow exam. Yes. That's why beta I'm doing 12th class portion only here. Yes, I got it. Student, from where are you watching live stream of physics point, student? Okay. Beta, all the best, student, for tomorrow exam. Keep calm yourself. Think carefully. Question, student. Be careful. I can say answering of any questions. Make sure, student, your presentation must be crystal and clear. Maintain rules like 20 words, 30 words, 150, like that. Beta, all the very best, student. Okay, have a look at questions. Non-conducting thin disk of radius R. Okay, fine. So disk is beta. Come to the point here. What I said, student, if you literally have a basics idea, student, God bless you, of disk here. So disk, what we can say, student, we have to move R. Student, we have to move R and take element dr as a ring. That is, student, I can say killer point for this kind of pattern of questions. Anywhere you will get this, so you can apply this thing. You have to move R. Student, you have to move R and take element dr. Student, you have to move R and take element dr. Student, you have to move R and take element dr as a ring. what's the name of this one here? You can see you have to move R and take element as a ring. It's an elemental ring. What, my dear? It's a elemental ring, right? So let us suppose here I can say I don't have a paper. Where it is? Yes. Just now I got from somewhere. There is one paper. Yes, beta. Have a look here. So beta, this is a paper, right, student? This is a paper. Okay. So this is a paper, right, beta? If this is a paper here, then what? If this is a paper, beta, if I'll apply force on this paper, so what you can say? This paper what? Become as a what, beta? You can say rectangle. Become as a what, student? You can say as a rectangle here, right? So beta, we'll go through this. So this is a ring, beta. If you will apply force, then student, what you can say? This ring act as a rectangle. This ring act as a rectangle. So what is the periphery of ring, students? What's the length of this rectangle? Is equals to periphery of the ring, which is nothing but, you can see beta, it's 2 pi r. And what is the width of ring? What is the width of ring? This is dr. This is what, my dear? You can see dr only. It's about circumference is equals to length of rectangle, and width, beta, you know, as usual, it's a dr. This is what, my dear? It's a dr. Okay, fine. What's up, beta, for this question here? So now I'm going to write, beta, what is the charge on elemental ring, students? So now I'm going to write charge on elemental ring. Charge on elemental ring is what, my dear? You can say which is equals to dq. So this is what, my dear? Sigma into dA, beta. Sigma into dA. So dA, beta, what you can write? Length into breadth of rectangle. So this is 2 pi r, student, dr. So this is 2 pi r into dr, beta. So dq is what? You can say sigma into dA. dq is equals to sigma into dA, right, student? Okay. Now we are able to find magnetic induction at center of a disk, right? So beta, I can say we have to also find here what is the effective current due to a rotation or circulation, right? So student, we have to find here, because yes, beta, this is a point at which you have to just keep in your mind, because if anybody rotating, so this current, we can say what? It's the effective current. Effective current due to circulation, student. This is effective current due to circulation of charge on element, right? So student, we can write here di. So di is what, beta? You know, yeah, this is what you can say dq by time period. And what is the time period, beta? I hope all of you remember here. It's nothing but 2 pi by omega. So di expression, students, you can write further dq, and t is what? 2 pi, beta. This is what remains omega only. This is what, my dear? You can say remains omega only. Okay. So and dq have we already found from here. So finally, beta, this we continue same step. So yes, beta, dq is equals to sigma 2 pi r into dr omega upon 2 pi, kopach. So So this is sigma into r into omega into dr. Now let's say party. Okay, so finally here, this is expression of, you can say, effective current due to circulation. Due to circulation, right, Vicha? Okay, so for this condition, I can also show this is direction of circulation of the ring, right, Vicha? Okay, so finally we can write expression of what? dB, because these all things we are doing for a small element. So now let's take snapshot, my dear. Yes. Now we can see what is the question, sir. Just look forward. So we can write it magnetic field at O. Magnetic field at O beta. You can say magnetic field at what? You can say center point. I'm just calling C because they mentioned magnetic field at C. So beta, magnetic field at C, student, magnetic field at C beta. This beta we have to integrate here. Magnetic field at C. This is dB. This is what, my dear? dB here. Okay. So dB beta, what we can write? This is, students, because it's a circular ring here. So what you can see? Magnetic field at the center of any circular loop, mu naught into I by 2r. So here beta, what you can write? Mu naught into di by beta z. This is what? 2x. Di we found here previously. Limit beta from where to apply here? 0 to r. So magnetic field at center C. This is mu naught beta upon 2x. And what is di, which is this is x naught, it's r I have taken. So from center it's r only, student. This is sigma r omega dr. Which beta? So now you can say, student, these are kopach. So magnetic field at center, you can write mu naught sigma omega by 2 integration of dr only and limit 0 to r. Limit 0 to r. So finally beta, I can write over here, magnetic field at center mu naught sigma omega r upon 2. So this is, my dear, you can see an answer of the first part of this question. In second part beta, what we wish to find? We wish to find magnetic moment. Student, we wish to find, this is magnetic moment. But there is a thing that if anything is rotating, in fact that ratio always constant. Student, that ratio always constant here, right? So beta, that is a ratio charge magnetic moment upon angular momentum. Beta, that is ratio magnetic moment upon a student angular momentum, which is equals to always beta fixed here for any rotating body, q by 2m only, forever fixed. This is what, my dear? Magnetic moment upon angular momentum here, which is what? Q by 2m, which is what, my dear? Q by 2m here. Okay, so we wish to find magnetic moment beta. We wish to find magnetic moment beta z. So this is q by 2m into beta angular, my dear, angular momentum. So it's nothing here. You can say q by 2m. It's L only. And what is angular momentum, which I'll calculate here further here. So this is magnetic moment is equals to q by 2m into L. And L is what, beta? L is equals to I omega. So what is I, beta? Moment of inertia of a ring about its center. Moment of inertia of a disk, beta, about its center here. I hope all of you remember. Which is equals to mr square by 2. So here you can write, my dear, mr square by 2 and omega beta itself omega only. Right, student? Just beta will go through this. So, bacha, further magnetic moment, which is q by 2m, and L beta you can write over here, students, m r square by 2 into omega. This m finished, so you can say q r square omega by 4. Q r square omega by 4. This q beta may be answer. This one also correct. S beta magnetic moment. This answer also correct, but it's depends on totally option, students. What options they are asking, right? So beta, you can this q you can also write here. This is sigma into area. Q beta, what you can write? This is sigma into area, right? So what is area, bacha? What's the area for a disk here? So you can see this is sigma into pi r square. So maybe it depends on option, student. This is also correct. Q r square omega by 4, or you can also write, student, magnetic moment is equals to sigma pi r to the power 4 omega by 4. So this is also correct, student. This is also correct, student, right? So just go through once and write here, write everyone, student. What I say, any doubt you can write, student. Any doubt you can write here. Any doubt, anyone, you can write. Any doubt, you can write, anyone. Anyone from all of you. Any doubt, you can ask me. Yes, beta. I hope all of you written a student. Okay. So now we can just move here. Next question, student. Right. So again, beta, I can say it's a good question which I solved. Okay, someone wrote, got it, sir. It's clear. Beta, God bless you. Are still night 11:20 and you are watching physics point, beta. I'm feeling proud of you, bacha. Okay. beta, just move here. Next question. Yes, beta. So what's question says? Yes, beta says. Figure shows a wire loop MN which carries a current I. Right. Bacha, I'll make a rough diagram first. Listen carefully, beta. Okay. So this is my dear. It's a rough diagram. Okay, it's complete loop. It's what, my dear? Complete loop. Right. Right. So beta, this is the loop. Yes, beta. So for this loop only current is flowing, which is I in magnitude. This point beta I can take care. It's center point O. This is center point O. Right, student? So here beta, what we have to find here? Find acceleration of particle at this instant. Student, find acceleration of particle at this instant here. Beta, something point here which you can take in consideration. This is O, this is M. Beta, current value, this is remains I, and this is M. This is M. So beta, I can again I'm going to read one question here. Figure shows a wire loop MN which carries a current I. A particle of charge Q and mass M is placed at a center O of a circle. Beta, there is one charge particle placed charge Q, mass M at the center of this loop. The particle is given velocity v along NO. Okay, NO. Along NO there is a particle velocity mentioned. Let us suppose along NO particle released in this direction with velocity v. Right. Find acceleration of particle at this instant. Simple here. We wish to find what is the acceleration of this particle. What is the acceleration of this particle at this instant? Okay, have a look. Let's tell you. First we can think here, what is the magnetic field at O? What is the magnetic field at O? Right. So you must know, students, this angle mentioned here in the question itself. This is 120 degree. This is what, my dear? 120 degree, right? So here beta, I'm going to write first what is the magnetic field at O. What's the possibility? So in this question, student, find acceleration of particle at this instant. Find acceleration of particle at this instant. Right, bacha? Okay. So now, student, I'm going to just solve this question here. So this is what, my dear? Step 1 here. Magnetic field at O. Magnetic field at O. Right. So I hope here all of you remember what is the magnetic field at a center of a loop. Mu naught into I by 2R. Mu naught into I by beta 2R. Then what you can say, this is the current carrying barrier. Have a look. This is the current carrying wire. Beta, this angle how much here? Tell this entire angle, students, which is equals to 120 degree, which is equals to 120 degree, right? Beta, you can see beta for this wire, entire beta radius is A. Let us suppose you can take this radius is R. So what this distance, perpendicular distance here? This perpendicular distance you can say R by 2. Student, this perpendicular distance, what you can write? This is R by 2, right? Okay. So, बच्चा जी, here I'm going to write magnetic field at this point. So this is minus mu naught into I by beta g 2R into beta g 1 by 3 plus beta. This is due to this current carrying barrier, because this is I wrote for loop. This is beta I wrote for loop here, because there is two things, one for loop beta and one for current carrying barrier. So this is student mu naught into I, mu naught into I root 3 by 4 by R by 2. I'll write again, bacha. There is not much space here. So magnetic field at O minus times mu naught into I by 2R 1 by 3 mu naught into I root 3 4 by R by 2. Right, student? Okay. So beta I can take it common from here. What? 2 beta cancel. 2 beta what I can say cancel here. Okay. So I can take common student mu naught into I by 2A. Mu naught into I by 2R, student. Magnetic field at O. This is mu naught into I by. This is 2R. Beta g root 3 upon pi minus 1 by 3. Minus student what? R 1 by 3R. Okay, so this is here we got basically magnetic field. If once we get magnetic field here, then better we can find force on moving charge particle. Force on moving charge. So step 1, student. Now I'm going to just solve step 2 for these questions. Force on moving charge. Student, force on beta g. This is moving charge at O. So I hope all of you remember force in a uniform and motional charge. This is F is equals to Q VB. So F beta, this is QV, and then if you just know I found mu naught into I by 2R root 3 by pi minus beta g 1 by 3. So this is beta we got finally our force. So step 3, student. Now I'm going to just take a snapshot, student. I hope you have taken. Yes, beta. Now student, I'm going to just write next step 3 beta for this question, which is nothing but acceleration. So what is acceleration? You can say this is force per unit mass. Force beta just now we found QV upon M mu naught into I by 2R root 3 pi minus 1 by 3, right? So this is, I can say, answer for the question here. So we have to find in these questions what is the system of charge particle. Charge particle released along NO, right? So again, but I can say it again here. One more good questions. Especially body. So pattern of questions here, I can say you can get idea more of the questions. Doing more number of questions. It's a hardcore truth. Okay. Now students, I'm going to do here, I can say rail problem. Yes, beta. Next question here, I can say this is what my dear. It's a rail problem. And students, I can tell this is literally very much useful. Yes, beta. This is literally beta. I can say very much useful. Like, no, what is the meaning of rail problem? You can understand first. Students, what is the meaning of rail problem? Rail problem. Okay. So student, for rail problem here, what you can say for a rail problem student, basically mechanical energy is what? Mechanical energy converting in form of electrical energy. That is, you can say, basic application of basically a rail problem. That is what, my dear, basic application of rail problem, right? So have a look here. What question? Beta, they ask like this question in JE 1988 also. Yes, beta. Not I'm telling exactly these questions, but pattern of this question is in JE Advanced 1988. Yes, beta. Already they asked. Already JE asked this student questions, right? So what question says here? Figure shows two smooth rails M and N. Okay, beta, be careful here. There are two rails. This is M and N. This is what, my dear? M and N. And there is one conducting rod. There is one conducting rod. There is one conducting rod. Right. Okay. Listen there carefully. Now we can see this entire setup student placed in uniform magnetic field. Student, this entire setup is placed in uniform magnetic field, right student? Okay, now which are connected to a current generator which supplies a constant current IS, right? Beta, this entire setup is connected to current generator device. There is, beta, I can say, kind of arrangement. There is what, my dear? You can see kind of arrangement, right? So this is the current generator device, and this device is creating a current over here. This is IS. This is what, my dear? Current generator device here is generating current. That is what you can say IS. That is what I can say. This is what IS, right? So you can still, this is directions of current. This is direction of current. So here also current here in this conducting rod. In this conducting rod, which body. So if this is current here, so you can say direction of what? Magnetic field. The direction of magnetic field inward only here. So directions of force on this conducting rod towards right. Simply beta I can just do like this here. I'm not able to do. Yes, this is the direction of beta current. So this is what force direction is representing. Right, student? This is what directions of force here. Okay. While PQ, beta its name I mentioned for which I have taken the conducting wire. A wire PQ. A wire or wire PQ. It's been a wire PQ of mass M lies over a rails which slides along the rails and fall over ground where friction coefficient is mu. Okay, fine students. I can see this is the PQ rod mass M. Student rod mass M, and this is what sliding over rails. This rod is what sliding over rails. Okay, and finally beta falls over a ground. This rod beta finally falls over a ground where coefficient of friction is mu. Find the distance over ground the PQ will slide before coming to rest. Okay, Acha, what you need to find the distance over ground, the PQ will slide before coming to rest. What my dear? Before coming to rest. Okay, just give seconds here. Yes beta, come to the point here. So here beta we'll go further here for this question solution. Yes beta ji. So we have to find distance basically. If this rod what finally falls over a rail on a ground, and ground friction is what? Friction coefficient between a rod and ground, that is mu only. So beta magnetic force first we can write here. Magnetic force on wire PQ. Beta in solution. Students, magnetic force on wire PQ is F is equals to, I hope all of you remember here, ILV. F is equals to, students, you can say ILV. Okay, beta there is one information here which I forgot. A you can take care. A is what basically length of, you can say, this PQ wire. Finally bit I can see this is coming out with velocity v, and if this rod here finally falls over here, so beta let us suppose this is uniform magnetic field. This rod finally comes over here, or you can see this much distance travel. This is x distance you can take, and finally final velocity of rod you can tell with 0. Final velocity of rod you can tell, my dear, this is what remains 0. Okay, so first beta I'll write here, already I said direction of magnetic force on this rod PQ. So this is what towards right. This is what towards right. Okay. So now beta I'm going to write expression of magnetic force on wire PQ is, I hope yeah all of you remember, F is equals to QVB and F is equals to ILB. So here is what I'm going to use, that is F is equals to IS into B, and this is A beta ILB formula. Simply beta I used formula beta I can say for ILB. Students, simply I used here formula of ILB, right? Formula of what, my dear? This is ILB, right? F is equals to ILB, my dear. Okay. Now students, I'm going to write here expression of acceleration. Because if particle gain force, then we can also write here expression of acceleration. So this is force per unit mass. Force per unit mass beta G. So you can say force is equals to IS B into A upon mass. So this is what, my dear, you can say acceleration. This is what, my dear, you can say acceleration. Okay. Linear speed, we can write what is the velocity particle gain. So beta we can use here v square u square is equals to 2a's. Initially beta particle goes to 0. Particle can gain velocity after some time here. So here student, I'm going to use your equation of motion third. V square is equals to u square plus 2s. This is remain 0 student. So this is v is equals to 2a and a beta just now we got b into is saturated is into a upon m into beta. What's the length? What's the length of, you can see beta I forgot to give you. L is the length of a rail. L is what? Length of a rail. Right. I can see if particle finally travel this much length, then gain particle gain speed. That is what, my dear, you can say. That is what, my dear, you can say. This is L only. So finally, beta, you got expression of force, speed of particle. Now here, a particle, if this PQ rod once hits the ground, so what you can say, beta, there is what on ground acceleration of wire PQ is what? Due to friction. Due to friction beta, there is a what's the acceleration, which is equals to minus mu g, which is equals to minus mu g. So beta, this now I can say you can take in consideration step 1. Now beta, I'm going to solve further part of this question, student. That is step 2. That is what, my dear, step 2 are further questions. So one thing beta pretty sure, because in particles once if this is the PQ, and this is the PQ conducting rod, once hits on the ground, so particle started retardation, or particle is retarding. A particle in the condition of retardation, so what we can say, velocity decreases. Velocity decreases. So here which acceleration for retardation, you can write minus times of mu g. Minus times of mu g. If wire comes to what? Rest after distance s, right? Because finally our particles come to at rest only. So beta here what we can find, distance s is equals to, this is what beta, v square upon twice of ar. Simple beta formula here, V square U square 2s. Okay, so V square beta just now we found here from here only V. So distance beta we wish to basically find here for these questions. So V square means you can say twice B is into A into L upon M into 1 upon twice of AR, and AR is what? Beta is mu here. No need to just take minus convention, minus is just meaning retardation. Then beta you can see these two cancel, right? So finally beta particle comes to rest before this distance doubled magnetic field into is into A L upon beta. This is m into mu into g. So this is the distance traveled by the particle before coming to rest. Before coming to rest, my dear. Jai Shri Ram, my student. Jai Shri Ram. Okay. So this is answer for these questions. So usually beta, I can say this is a good question, kind of questions here. So be alert. I'm very happy to see beta. It's time around 11:45, and you are watching physics point. Yes, beta. I'm very happy to see your live stream of physics point. Now, student, have a look at next question. Yes, beta. So I can see beta magnetism, EMI, and ACR. Usually magnetism and EMI very much similar. Very much similar. That's why beta I took common classes for all. I'll do few questions based on, I can say, student basically AC also. But first I'll finish at this target, EMI and magnetism. So it have to look at next question. What's question, student? Okay. Have a look beta. So this is x and this is y. This is x beta and this is the y. Figure shows the trajectory of a charged particle with a charge q of mass m in a uniform electric and magnetic fields. Okay, both fields is there beta. So you can take electric field, student. Electric field along x-axis. Electric field along x-axis beta. And magnetic field here I can say in positive z direction. Yes beta. This is the direction of magnetic field. This is what, my dear? Direction of magnetic field. Okay, very much good. Now beta, I'm going to release a particle from here only. Now students, I'm going to release a particle from here only. Particle from here only. So what's the speed of particle? Which is equals to v. This is equals to v. So this is what, students? I can say A. It's everything mentioned in the diagram only, which this particle beta finally hits. This particle finally hits over here, and it has the velocity of this particle. You can mention the questions here, which is equals to 2b. This length is mentioned, my dear, which is equals to 2a. Which is equals to 2a. Okay. So beta, in this is you can see beta charge q mass particle here only. Beta charge q mass here only, but now particle finally hits over here. So this is remains charge q and mass m only. There is no change at all. Okay. What question says, my dear? With a charge plus q mass m in uniform electric field and magnetic field, the particle enters in a region at a point P. Particle enters in a region at a point P and Q. beta, this is the particle enters in a region P and exit at a point Q. This is P bacha, this is what you can see Q. Right. The particle enters in a region at point P with speed V and leaves with at a point Q with speed 2V. Find the power supplied by electric and magnetic field to the charged particle at point P. Okay, very good here. Interesting questions. Yes, beta. Very good here and very much interesting questions. Okay, beta, listen carefully here. From particle P to Q, work done by electrostatic force is we can find, but there is no work done at all. You can say due to magnetic force because you know QVB. So for this is I can say beta first click for this question here. What work done by electric force, or you can say electrostatic force, work done by electric force. What beta? You can write here what is work done. It's beta force into displacement or distance here. So F is equals to QE. F is equals to, my dear, you can see what? Q here. So finally this expression we got work done due to electrostatic force on charged particle, which is what, my dear? QE into A. Which is what, my dear? QE into A. Okay. Now I'm going to apply here. You can see step 1 for these questions. Step 2 here. Using concept of, my dear, using concept of work energy theorem, right? So this is what is doing. Work done total is equals to beta G, change in kinetic energy here. So what's work done total? Only due to electrostatic force, magnetic force. Because magnetic work done due to magnetic force always 0. So this is what, my dear? QE into 2A, QE into 2A, which is equals to half m beta. This is 2V whole square minus half m into V square. So this is, students, 2QE into A is equals to 2 to the 4 here, 4 minus 1, 3 by 2. You can say beta 3 by 2 m V square, 2 to the 4 here, 2 to the 4. So you will get a value of electrostatic force 3 m V square by 4 QA by 4 QA, right? So this is what we get here, basically value of electrostatics, or you can say it's electric field. It's what beta? Electric field here. So power supplied by electric field. Power supplied by what beta? You can see electric field here. So I hope all of you remember here. Yesterday also I used this formula. So power beta due to electric field. Power beta due to what? Electric field. So what is power beta? F into V. F beta, you can say due to electric field. Q into E into V. E beta we already got here. So you can write this is Q, and what is beta? Here 3 mV square 4 QA into V beta. You can say for these conditions Q can say 3 by 4 mv square upon A into B into बच्चा पार्टी B भी multiply further here, so 3 by 4 mvq by A power due to electric field, and it has here you can write here power supply by magnetic field, power supply by magnetic field which is equal to 0. Why 0? Because work done due to what? Magnetic field is always 0. Is always, my dear, what you can say here, this is what remains 0. So this kind of question is very common format here. Just take a snapshot and write down the chair. Yes, beta, take a snapshot and write down the question. Yes, beta, it's highly required here. And these are, I can say, beta, where if in 11th 12th class, anywhere, if you are using 11th class concept, so you can understand, you can easily tell, yes, it's a good question. Because if anywhere, if you are getting like application of this thing, so you can understand like this. Okay, now bacha, I hope that you have taken snapshot of this question. Now student, have a look at next question. Have a look bacha party, this is the next question here. Okay, so what's the next question, student? This a circular wire loop of radius r. Student, this is the circular wire. This is what, my dear? Circular wire loop of radius r. Loop of radius r can withstand a maximum radial force F naught, right, in it before breaking. Okay, a particular mass m and positive charge q is sliding over the wire. A magnetic field B is applied normal to the plane of the wire. What maximum speed of the particle can have before loop breaks? Okay, very, I can say, common question, students. You can take care. This is what? Magnetic field. This is what, my dear? Magnetic field. Okay, circular wire of a loop radius r can withstand maximum radial force F naught in it before breaking. Okay, fine. But that is here. I wanted to make one diagram. Let us suppose what we wish to find it, velocity maximum. That's all. This is the point here. So at this point, I'm calling this is the speed of particle. So I'll make it as this diagram here only. So just think here, this particle is in contact. So how many force responsible to avail centripetal force or centripetal acceleration? So this is what, my dear? The particles over here. Particle motion beta, that is V. This is V, student. Particle has what? Students, you can write over here. mv square by centrifugal force here. I hope all of you know very well. If any particle which is moving on a circular path, so centrifugal force always away from the center, students. mv square by r, beta, I can say inward directions here, or you can say centripetal acceleration, which is availing by magnetic force q b, and beta what? One more normal is there. One more normal is there for revolution of beat in wire. We use here along radial direction. Now we can see system here in radial direction. This is remains balanced. So students, here right here along students along radial direction. This is MV square by R QV plus M. Right. Students, for this condition here, they are living. They are what? Students, you can say living here. So with a finally you can write here for this condition. This is MAV square by R minus QBV. But there is one more point here that is mentioned in these questions. Right, Amita? There is maximum radial force. That is what? F naught here. So you can see minus F naught, which is equals to 0. So students, here we can write here velocity maximum, which is equals to QB plus minus Q square B square is because this is quality equation. This is what we have finally a quality equation in terms of V, students. So finally you can solve. I hope all of you know our formula here. V is equals to means x is equals to minus b plus minus under root b square. Under root, which is what you can see. This is b square. So this is q square b square minus 4ac is minus minus plus 4 f naught m upon r. So this is beta formula as I applied here. Upon which is 2a. So twice into m by r. So whatever is you will get answer here for the questions. This is expression here. So just you will face this question in the paper hall. We maintain patience. It's highly required because if there is no patience at all, so it's very tough to manage. Yes, better. It's very tough to manage here in the paper hall. So be alert. Right? Okay. Fine. So it's not tough at all. It's a normal mechanics. You can just think in the questions. Because this pattern of question literally it's very common question in the classroom program. Yes, the classroom program. It's already okay. Have a look at next question. Yes, beta. Have a look at next question. What is the next question here? Vowel of radius is all problem. We are all problem also very much useful. I can say student in NLM here also all problem. Yes, come here. It's a good question. So beta first I'll draw diagram here. A bowl which is students magnetic field. A bowl which is placed in uniform magnetic field, which is placed in uniform magnetic field, right? So first student I'll make bowl yes beta. You can see also this point as a radius. Yeah, this bowl I'll make FBD here only, right? Yes, FBD of bowl, FBD of bowl. No, yeah, for better clarification, you are at physics point. If you are at physics point here, here I'm always try to give you easy explanation of any questions. This is you can see power. This is the power, right? Okay. Figure shows fix all what's about radius r in which this radius is r in which from its rim, a charged particle of mass m, charge q is released. Charge q and mass m beta what you can see released. You can see which there is a particular mass m, charge plus q, they released. After any time t, you can take a particles comes over here. Literally, it's not tough at all. Okay, so students take as a consideration particle is making angle theta. Particle is making angle theta from vertical. Student particle is making theta from vertical. Okay, now you can easily see this is what normal. This is what normal charge beta mass m. So you can say mg acting in this direction. What my dear, mg acting in this direction here. So this is theta beta. You can easily say this is also remains theta. This is also remains theta beta. Okay, charge particle in motion here. So you can write this is what a direction of, not exactly beta, direction of QBB, direction of this is Q BB, this is what my dear direction of QBB. Okay, fine. This is a normal force here. This is what beta normal force here. So if you can also take beta component of this R, right? Because particle motion are like this. Particle motion is this here. So we have to also write here mv square, right? mv square by r. So you can see finally a particle how much we can simply beta we can apply. Particle has what maximum potential energy and now convert it in terms of kinetic energy. In terms of kinetic energy, because particle once arrived over here, so particle gain here velocity. So from work energy theorem, student from work energy theorem, here easily you can write, student from work energy theorem, here easily you can write particle has what initial potential energy. This energy what beta converted in terms of kinetic energy. So this is r, you can say r cos theta, and what you can say this about r sin theta here. So beta, you know, entire length is r. Entire length is r here, right? So what you can see this much distance here, this much distance with a party. Yeah, entire just I'm feeling now. Beta, I'm just teaching you work power energy here, literally. So beta, this entire distance r cos theta here, you can just take component r cos theta. So this is a distance here from here to here. So particle has what initial potential energy. Particle has what initial potential energy, right? This energy converted in terms of kinetic energy here. So using weight, using work energy theorem. Again here you can see kinetic energy initial, potential energy initial, right? Kinetic energy initial plus potential energy initial is equals to kinetic energy final plus potential energy final. You can say particle don't have like beta kinetic energy initial, so particle has initial potential energy only. This is mgr beta g cos theta, which is equals to half mb square, which is equals to half mb square beta. This m finished it. So you can write v is equals to beta 2gr cos theta. V is what my dear? V is equals to root of 2gr cos theta. Now here we wish to find normal force. We wish to find what? Normal force. Very easy to write here. right? So again here I'll make one more ability. Yes, beta. So listen there carefully, everyone, because this is what beta ji ability is the same, because ability is the answer. You know what is beta? I can say ability. Physics is what language of ability. So we remember ability must be crystal clear. So we wish to find normal here. So you can see normal over here. This theta beta what theta here from vertical. This is what my dear mg here. This is what theta. Same direction beta. You can say qvb. So this is what beta theta here. So this is remain theta. You can take component of mg. Mg belongs to beta. Mg belongs to quantity vector. So you need to take component here. So this is beta, you can say mg cos theta. Simply you can just equate beta these forces. Simply beta you can equate these forces here. One more force over there, what you can see centrifugal force, which is mv square by r. Beta just equate these all forces. So normal is equals to mg cos theta plus mv square by r plus qbb plus qbb. Yeah, v value beta we already found here previously. Root of 2gr cos beta. Here bacha we already found here. V is what? Root of 2gr cos beta. So beta I'll use beta here only. So normal is equals to mg cos theta plus student v square here. So what is v square? 2gr cos theta. This is 2gr cos theta upon r plus qbb. Right. Beta you can see these are finished. These are finished. mg cos theta plus 2mg cos theta. So normal you can write my dear 3mg cos theta plus beta qbb beta, and v is what? Root of 2gr cos theta plus beta, root of 2gr cos theta here. So finally beta you got value of normal here, which we wish to find, which beta we wish to find here. So we are learned students, paper is not tough at all here, but you know questions why it's good, because you can see easily how application of mechanics. So mechanics really I'm talking about advanced. Rarely they can ask any question directly, but I'm pretty sure application of mechanics is very much. Without knowing mechanics tools basic, can't learn your 12th class. It's highly required. So if you want good knowledge in 12th class, you must make a very good grip on, I can say, Bichaji, for 11th class concept. If you don't have a good grip on 11th class, then yeah, it's very tough. Then it's very tough here, right, to discuss the point. Okay. Coming to one more questions here. After it, beta, I'll bind up the class here. Yes. This is one more beta. I can say last questions for today class. A particle of charge Q and mass M enters a uniform magnetic field with velocity 6 I cap meter per second. The width of magnetic field region is mv by 2 qb. Find the velocity vector of particle when it comes out from the field. Find the velocity vector of particle when it comes out from the field. Simple, yeah. It's a very question, easy, and I can see it's a standard question, student. Yes, beta. Have a look at these questions. So what's question says, student? Have a look. A particle of charge q. Yes. But I can take in consideration this is what uniform magnetic field region. This is what my dear uniform magnetic field region. Uh, Distance between, you can say beta, this region is nothing but it's r by 2. It's r by 2. Let us say beta from here charge particle q and mass m entering. Charge particle q and mass m entering from here, and this is what you can say with velocity v. This is what you can say velocity v. We have to find basically, or I can say that is find the velocity of the particle, right? So we first know how much particle got deviated. How much particle got deviated, that is the first thing you need to find. But everywhere you can take care magnetic field remains constant. Magnetic field remains constant. Okay. So beta particle going in this direction here. We remember it's not tough at all. Yes, beta. So we have to first ensure this is what directions of beta, you can say magnetic force. So particle will take a turn like this. That is also point how particle can take a turn in an uniform magnetic field. That is what you can say directions of magnetic force. So we are pretty sure particle got deviated from here only, right beta? Particle got deviated from here only. So this is we wish to find this velocity here. So we have to must find here what's this angle. Okay, this is, students, you can say an angle of deviation. This particle will definitely I wanted to go like this, but particle got deviated this much. So this is here, we'll go through this how this is. This is 9, this is 90, this is 90 minus this is 90. But what we can see, this is what remains theta here. This is what you can say remains angle of deviation. Angle of deviation which are right. Okay. If any particle are making a circular path in uniform magnetic field, so student, what's the radius here? Radius is equals to, I hope all of you remember, otherwise I'm writing here, R is equals to MAB by QB. R is equals to what, my dear? MAB by QB, right? This is the radius here. Okay, the width of the magnetic field region, that is beta, D is R by 2 mentioned here. So we have to find here this formula, angle of deviation. So what we can say, this is what perpendicular, this is what you can see perpendicular upon here OH, perpendicular upon base bacha. So this is, you can write here, R is the radius of R only. So students, here I'll write first angle of deviation of particle, angle of deviation of particle. This is what sign of deviation here. So it's what D upon R. D beta already mentioned in this question, student. So sign of deviation R by 2 by R cancel here. So sign of deviation is equals to 1 by 2. This implies angle of deviation is equals to 30 degree. Angle of deviation which is equals to 30 degree beta. Okay. Now here we wish to find velocity. We wish to find what? Velocity here. So easily consider. So this angle is known for us. So this angle of deviation you can also write. This is what? 30 degree. So finally particle motion is V. This angle is what? 30 degree. So you can write beta, this is Vx is equals to V cos of 30 degree beta. This is Vy V sine of 30 degree beta. So Vx you can write root 3 by 2V, and V by beta you can say V by 2. V by 2. V cos 30 here, root 3 by 2. Now beta say okay, and V beta by 2, this is V by 2. So V beta mentioned in this question here. Velocity is mentioned, student. This is 6 I meter per second. So I'm writing the form direct velocity in vector form. Velocity net in vector form, student. This is root 3 by 2v plus v by 2. So this is I cap and this is j cap. Yes. So beta, I can say this is the questions here which you can keep in your mind. Beta, as I can say multiple time, not a single time, student. J already asked this angle of deviation. Yes, beta. J asked here this angle of deviation. There is a possibility they didn't ask this pattern of questions. They can ask. They didn't ask this pattern of questions here, so there is a very high probability. Definitely they can ask. Definitely they can ask. So being I can see a student, very happy to see all of you. Those I can say watching physics point live stream till now, right? Okay. Yes, beta. Usually I'm looking these kind of questions more. That is what student. I can say it's a J 2019 question. Literally, it's a very good question. Yes, beta. It's a very good question. Yeah. I wanted to prove it. That is one more last question for today class. Yes, this is beta last question. Literally, beta, there is no change. I'll not take more class. I'll stop live stream about this after this question solution here. So what question shows you, students? There is a diagram here mentions. We'll go through diagram, student. Yes. Fine. So there is inductor. There is inductor. And this inductor is connected to capacitor, right? There is switch system, students. Switch initially open. There is one more capacitor is there. Very good question here. Yes, beta. It's very good question, students. So this is beta what you can see capacitor. Both identical with C and C. Figure shows here I can see circuit in which left side capacitor is charged to a voltage V0. If at t is equals to 0, switch is closed. Find time dependent voltage in both capacitors. Time dependent voltage in both capacitors. Okay, fine. So students, for this condition here, this is inductor. Student, inductor here. So inductor beta, inductance, I'm considering L. Capacitance beta, this both are identical. So I'm calling this is also capacitance C. This is also capacitance C. Right. But I can take in consideration beta. This is plus charge Q. This is minus charge Q on capacitor there. So here beta we will go through here. I can say like loop law. Charge no beta, I know. Charge, students, remains conserved. Charge remains conserved here. So here beta you can write for, because this is connected. We have to just think about charge transformation and charge transfers to each other after closing switch here. So this is plus Q and this is what? Minus q. Now students, for this charge, this particular, you can say what's the charge over here. So this is what, students? Q minus q. In these conditions, you can say q minus q. Q minus q. Q minus q beta and minus what? Q minus qr. Just keep in your mind. Beta, time is, I can say if time is 0, so it's closed. Students, you can take in consideration. If time 0, then switch is what? You can say closure. Right, switch is closed. Okay, so beta, we can find an energy stored in what? Beta G for entire setup here. Energy stored. Because once we'll heat here started. So what is beta G? I can say this is situation here for time 0. So after you can say after time t, energy stored in circuit is, because energy stored here also, and inductor also. After you can say beta time t, or you can say at time t, right? Energy stored in the circuit is energy stored in the circuit is. So this is what, my dear? A is equals to 8 q square by 2c here. I hope all of you remember. Q squared by 2c plus student q squared by 2c half L beta is beta. This is, I can say beta for this capacitor. This is beta what? You can say for this capacitor here, and this is what? Half L square. This is energy stored in the inductor in form of what, beta? Energy stored in the inductor in form of magnetic field. So just keep in your mind, student. Okay, now beta, just differentiate in terms, because we wish to find time dependent voltage in both of the capacitor. So beta, just differentiate both sides here. Student, differentiate both sides. Yes, beta, here you can differentiate here both sides with respect to time t. With respect to what is time t here. So this is differentiate beta with respect to time. Differentiate beta with respect to time with charge. Okay, so beta, this is come this side here. So we can say twice capital Q minus Q minus I cap upon 2C. Then beta, this is what you can say 2Q by 2C into it, what you can say L only. What is you can say L only here plus half L I square. Half L I square beta. So this is, you can say again 2I di by dt, right, which is equals to 0, which is what, my dear? Which is equals to 0. Further students, I can solve here, no need to worry. So what we got the result as a result, this to finish Q minus Q upon C. Yes beta, this this is near simple. I can 2 beta again cancel here. So plus Q into L upon C plus 2 again cancel here. So we can say I di by dt, which is equals to 0. Which is equals to 0. Okay. Further student, we can write here, I can say what's the charge on inductor, charge on resistor, right? So this bit will get your common data. Behalf of this result, we can write charge individually. So students, charge on inductor Qi2 plus Qi2 sin omega t plus alpha 1. Students, sin omega t plus alpha 1 and sin omega t plus something here. What we can say? Cos theta. So we can write charge on inductor, which is equals to Qi2 plus Qi2 beta cos yes beta. This is charge on inductor. Now beta I can write next here, that is charge on beta resistor, charge on beta what resistor here. So this is Qi2 students omega t plus alpha by 2. So this is Qi2 beta minus Qi2 cos twice upon LC into time. So beta we used to find here, I can see also beta in point number 3, potential drop on capacitor. So this is QL by C. Q is what? B0 by 2 1 plus cos of root 2 by beta, what again LC here, LC into time t. Beta last expression here, it's basically you can say here LC oscillation. What mean you can say simply it's about LC oscillation. So potential as a function of R, this is what my dear, this is what a student, you can say QR by C, which is equals to B0 by 2 1 minus cos of beta twice of LC into time t. Finally, picture party, just differentiate one more time here. Differentiate picture one more time. This is equations here, which I differentiated here only. But this same equation differentiate once again. So we can get picture d 2q by dt square twice upon LC plus q upon LC, right? So same thing beta, this it's a double derivative. It's a what my dear, double derivative here. So just keeping in mind beta, just compare beta this from here only. d2 by x square plus beta, this is omega into y plus c. beta baby is to find at mean position. Baby is to find student at mean position. So this is what, students, you can write c upon omega square. C upon what we said, omega square here. So finally we says baby is to find what's a charge. So charge beta at a mean position. Yes beta, yes, I'm going to write here finally. Students, what's the displacement of particle at mean position, which is equals to beta c upon omega square, which is equal to what, my dear? C upon omega square, right? Charge at beta, you can say mean position. This is q by 2. This is q by 2. I hope you are all of remember your omega LC oscillation. So twice upon LC. Twice upon what? Because you can say LCR. So we have to find time period of dependency of the voltage in both capacitors. Right. So finally we got answer of this question. This omega is equal to twice upon root of LC. Omega is twice upon root of LC. Right. So this is for this today class here. I'll discuss something more numerical with more things here. If possible for this concept, otherwise I'll start next concept here. So this is all about beta, I can say, today class. God bless you all. All the very best.